Part 1. Intro to Equilibrium. Equilibrium. In a transition reaction, other reactants get turned into product if we assume that there are no excess. So, if there's no excess, all reactants turned into product. And these transition reactions that proceed in only one direction are said to go to completion. And these transition reactions are represented with single arrows. In an equilibrium reaction, this is not the case. Okay, it's a little bit different. The reaction sort of stops partway through and reaches the different equilibrium, okay, and turn into the transitional products. A reversible reaction is one where the reactants and product exist in a state of the equilibrium. So, reversible reaction, at some point in this reaction, it will reach a state of the equilibrium when the speed of the forward reaction and reverse reactions are equal. Okay, and reactions that can proceed either direction are said to be reversible. Okay, so we can actually say that all equilibriums are actually reversible. And reversible reactions do not go to completion and occur in either direction. And we represent these reversible reactions with this double arrow. Okay, so far we now know what is meant by the transitional reaction and reversive, okay, which means equilibrium reaction, right? So in a transition reaction, we use a single arrow from the reactant to product to represent how the reaction goes. In the equilibrium equations, we are representing these reactions using double arrow, and each of the arrow only has a single-sided head. Okay, so for the transitional reactions, the arrow has the double-sided head, but for the equilibrium, it has two arrows. Okay, and they have only single-sided arrow, just like this. Okay, and the unit we make a lot of reference to the speed of the equilibrium is the forward reaction. So forward reaction means the reactants becoming products. Okay, so in this case, the arrow will look like this. Okay, you can see that the arrow goes to the reactant side is longer than the one goes to the product side, right? If we have a back reactions, back reaction means the products are becoming the reactant. In this case, the arrow goes to the product side will be much longer than the arrow that goes to the reactant side. This is how we represent or the reference the reaction type, okay, or the speed of the reaction. Okay, so let's consider we have a bromine, okay, bromine gas. Okay, bromine gas is volatile gas or volatile liquid. Okay, we can say volatile liquid. Let's say it's volatile liquid. That means its boiling point is close to room temperature. So let's say we have like Br2 liquid in a closed system. Okay, so we think it's in the closed system at room temperature. Okay, when we have it at room temperature, there's a lot of the particles, okay, molecules of Br2 bromine gas that has enough energy to escape from the liquid state, right? Which is in the liquid state to the like gas state, okay. Or you can say like it has enough energy to escape from the liquid state to form vapor, okay, to in the process, right, to escape this state, okay. When it goes from the liquid vapor, that means they have a condensation going on. It means they have a evaporation going on, okay. When the evaporation happens, okay, if it's not closed system, if it's open system with the Br2 liquid, what happens is they're going to escape like this, okay, and they're probably going to escape the container too. However, if it's under like closed system, okay, let's say it's a closed system, when this happens, what's going to happen is they're going to evaporate, okay, but in same time they're going to collide. I mean, like they have no space to escape, so they're probably going back down, and when they collide with the surface of the liquid, they lose energy, right? Because they give energy to the liquid. Okay, so they're going to lose the liquid, and when that happens, it becomes liquid in the process. Okay, in the heating process. So that means the vapor, the gases, will come back to liquid state, and this process we call it condensation process, right? Okay, so when we have a condensation and evaporation happens in same time in a closed system, so when we have a condensation and evaporation happens in same time, eventually when that happens, eventually the speed of the evaporation and speed of the condensation reach same point, means they're going to be equal at the end. So at this point, there will be no net changes in the amount of the liquid and gases in the system. And when that happens, we say that the system has reached equilibrium. Okay, and as you know, and all this stuff can only happen. All this stuff can only happen in closed system, as I mentioned. Okay, because they need to trap everything. Okay, and this is how you explained the physical systems of the equilibrium. So chemical equilibrium also exists when forward and reverse reactions and processes occur at the same speed. The concentration of the reactants and product is constant at equilibrium, means they're not equal to each other and they're just not changing. The speed of the forward reaction is equal to the speed of the back reaction. That's the reason why the concentrations become constant. At equilibrium, these are not zero, even though it looks like it on the graph. Okay, so let's check the equilibrium graph. These are the equilibrium graphs. Okay, so you can see that when the concentration change becomes constant, we say equilibrium is reached. So in the first graph, okay, we can see that there was changes with the concentration of the NO2 and N2O4 until a certain time, and from starting this point, we can see that there is no changes with the concentration, right? So actually the concentration remains the constant right now from at this point. Then we say it's right now at this point the equilibrium it has achieved, and then we have equilibrium mixture. However, if we reverse this reaction and okay, then if we if we are explaining this graph again with the speed, okay, when the speed of the forward reaction means forward means it's going to the product side like this, right? And the speed of the reverse reaction, okay, becomes the constant or the same over the time, then we say the equilibrium is achieved. Okay, these are the two ways of the representing the chemical system of the equilibrium. Okay, so now we know the graph of the equilibrium. So now we need to know how to explain the equilibrium positions. Okay, and equilibrium positions changes depends on how much product and reactor there are at the equilibrium. Okay, and it can shown with the double arrow. If there are more product than reactants, the products are said to be favored. Okay, that means if it has forward reaction is happening, right? For reaction. And if there are more reactants than product, then the reactants are said to be favored. So in case of the reverse reaction, we have the products favored condition. Okay, so there are two types of the equilibrium reactions. First one is homogeneous equilibrium. Second one is heterogeneous equilibrium. We say we have homogeneous equilibrium when the reactants and products are all in the same phase. And example reaction can be two. Let's say we have NOBr gas, equilibrium state, to gas, and Br2 gas. And you can see that their phase is all gas, right? So in this case, we say we have a homogeneous equilibrium. Okay, so we say we have a heterogeneous equilibrium when the reactants and products occur in different pace. Okay, the example can be PbCl2 solid equilibrium state, Pb2 plus aqueous plus 2Cl minus aqueous. Okay, so we can see that in this case, the reactant is in solid phase, the products are in aqueous state, so we say this is heterogeneous equilibrium. Okay, so equilibrium, to explain the equilibrium or to know whether reaction is in equilibrium state or not, we need to know the characteristic of the equilibrium states. There are 5 features that equilibrium state have. Okay, the first feature is a dynamic. Second one is achieved in the closed system. Third is concentration of reactants and products remain constant. Fourth is no change in macroscopic properties. And the last is can be reached from the either reaction. It means both forward and reverse reaction need to happen, right? So these are the characteristics of the equilibrium state that you need to remember to identify the equilibrium reactions. So remember, the concentration of the reactants and products are constant, but do not have to be equal. The proportion of the reactants and product in the equilibrium mixture is referred to as its equilibrium position. And reactions where the mixture contains the predominantly products are said to lie to the right, and the reactions with the predominantly reacts are said to lie to the left. Means if it goes to the if the lie to the right, okay, lie to the right, this means it favors the product, right? then its equilibrium sign will look like this. Okay, if it's favored to the left, okay, this means it favors reactant. Okay, and this the equilibrium sign for this type of the reaction will look like this.